Software Engineering Daily is sponsored by Hired.com. If you're looking for a job, Hired.com is the place to start. I've used it personally, and it is an excellent service. Software engineers and designers can get 5 interviews in a week with top companies. Go to Hired.com/softwareengineeringdaily for a $4,000 bonus upon accepting a job. Thank you, Hired.com. Gérard Huet is a senior researcher at INRIA, the French Institute for Research and Automation. Gérard helped develop the Camel programming language in the 80s and has a variety of other accomplishments in the world of computer science. Gérard, welcome to Software Engineering Daily.
Thank you. Hello.
So this is Functional Programming Week on Software Engineering Daily. I'd like to start by talking about Camel, which you helped develop while you were leading the Formel project. What was the Formel project?
The Formel project was concerned, so it's a little bit of a joke. Formel in French is the adjective that means formal, so it evokes formal methods, but it's also a joke on 4ML. So in a sense, the project was devoted to the ML programming language. But initially, the goal was to develop proof techniques and a proof assistant. So this was my long-range goal. It's to develop theorem provers and proof assistants in order to develop mechanical mathematics and systems for automating proofs of programs.
So what is ML?
So ML stands for meta language, because initially it was the meta language for developing proofs in the LCF proof assistant that was developed by Robin Milner and his team at University of Edinburgh in the 70s. So LCF means logic for computable functions. So it was a special proof system. You could construct basically natural deduction trees in a specific proof system that was due to Debacker and Scott, so relying on notions of denotational semantics.
Okay, so before we get too much further into ML, I'd like to set some context. What was going on in the world of computer science in the early 1980s, around this time?
Well, the world of computer science is very big. So you had like numerical analysis using Fortran. You still had the use of COBOL, and you had the start of system programming language. And Ada was on and so on. But people doing non-numerical applications, such as artificial intelligence or computational linguistics, typically, were using LISP. LISP was a kind of ubiquitous programming language at the time, although some people were aiming at Prolog, which was in its beginning, in the beginning of 80s.
Why was Lisp so popular?
Lisp was popular because it was very easy to use since it had an interactive implementation. So the training time was very small. You would just sit at the interpreter and then type in and then get your results immediately. So it was easy to learn. Then it had dynamic data structures with a garbage collector. So you could create trees and possibly huge data structures without worrying about allocation. So it was a lot of ease.
Okay, interesting. So as you mentioned, ML was the meta language of the LCF proof assistant. So what was the purpose of proof assistants?
The purpose of developing automation of mathematics was, besides the assistance to mathematician, it was mostly for doing proofs of correctness of software. So this was, and this is still the main stumbling block of software. It's correctness, safety, all kinds of considerations for which you want to have confidence in the output of your software. And personally, I've always thought that software engineering was of rather poor quality compared to hardware engineering. Because in hardware engineering, any mistake will show very quickly. Whereas in software engineering, people could get by with bugs that were hidden. And since we were concerned more and more with the safety critical systems, we needed to have proof assistance.
Do you think there's an upper bound for the level of complexity you can create a proof around? I mean, because that's the thing I see with software is like sometimes your software project can just get so complex you can't have a proof of correctness around it.
You have several measures of complexity. One is size, but this is not the main problem. The problem of size is encompassed by modularity. So if you know to write modular software, and if you know to do modular proofs, then and if your the mathematical material associated with your programs is somehow linear in the size of the program, then big can be encompassed just by modularity. There is another kind of complexity, which is intrinsic complexity. For instance, if you take volume 1 of Knuth, the art of computer science, the first program he gives, actually, is a program for generating primes with the Eratosthenes sieve. And it's a very simple, small program, but there is some optimization. And in the footnote, he said this optimization is valid. But actually, the validity of this optimization relies on a very tough theorem of number theory, which is called the Bertrand postulate. So here you have an example of a very small program and a very small optimization for which you need to develop a huge mathematical proof in order to prove its correctness.
Okay, fair enough. Well, so what were people saying about functional programming around this time? Was that in the lexicon? Did people have the term functional programming?
Well, first of all, functional programming is kind of ambiguous. All that LISP, in some sense, allowed functional programming. You had a construct that was called lambda, which was how to make a procedure out of an expression. And so this looked a little bit like the lambda of lambda calculus. And it allowed you to define functions, but functions with dynamic binding. So this is not really the correct implementation of the kind of minimalistic functional programming language that is lambda calculus. There are two ideas in functional programming. One is the ability to manipulate functions as opposed to just first-order values like integers, booleans, and lists. and to have a function that can be arguments of other functions. So this is it's a way of having more power with your procedures, because you can have reflection, you can have sophisticated argument passing your functions to functionals and so on. But what is mostly advertised in functional programming is actually applicative programming. Applicative programming means that the result of your computation does not really depend on some kind of state, like the state of some global memory. It's more like a mathematical evaluation of an arithmetic expression. So we like applicative programming for at least two reasons. One reason is that it's easier to reason about applicative programs because they are static expressions. So the usual mathematical techniques apply. You don't have to take care of a complex state. That's one aspect. And the other aspect is that it's easier to parallelize. Now, if you take seriously this idea of applicative programming, and if you are some kind of extremist, then you will reject every kind of imperative programming. And this is not very convenient. It's a bit of an extremist attitude. So both LISP and ML were a mixture, actually, of imperative features and applicative features.
Okay. Well, so let's get back to the story of the evolution of the Camel language. So there were some projects related to ML that served as the eventual inspiration for the Camel language. What were these inspirational projects, and how did they lead to the development of Camel?
Okay, let me tell you the anecdote of how ML came in the picture at our group at INRIA. As I said, I was interested in proving, and I had worked on further proving, I worked on equality reasoning and rewriting, I worked on proof by induction, and in the beginning of the 80s, I thought that the time was ripe to try and develop a proof assistant for higher order logic as some kind of long-range effort. So my concern was to use for the implementation of this proof platform a language that was as clean semantically as possible. I was a great fan of LISP, of course, but LISP was error-prone, and LISP was such a mixture of imperative and functional that it was very hard to do any kind of efficient programming in LISP. For instance, in LISP, you have the fundamental operation replac A and replac D, which are destructive operations on your data structure. So in this, very quickly, if you do this kind of operations, you wind up with a big dish of spaghettis, and you don't know what is static data, you don't know what is dynamic data, so the garbage collector ends up roaming the whole universe of your data. So it's better to have a stronger static analysis. So I was kind of shopping for the best programming language in 1980. I went to see my colleague Jean-Jacques Lévy, who was a specialist of lambda calculus, I asked him, Jean-Jacques, what do you think is the best language for programming this endeavor? And he said, oh, why don't you try ML? And I was very surprised because I knew a little bit ML, this specialized language for proofs inside the LCF system, but I did not think of it as an implementation language. The LCF was implemented in LISP. It was a big piece of LISP, and part of it was an interpreter for this language ML. So using ML itself as the main programming language of the whole proof system was quite puzzling for me. So I went to see another colleague of mine, Gilles Kahn, who was a very respected senior scientist, and I asked him, Gilles, what do you think? Jean-Jacques suggests ML. Do you think it's a good idea? And Gilles said nothing, but a few days later he came back with a mic tape with LCF, and he handed it to me. See, at the time we did not have networking facilities yet in Europe, so we were exchanging software by mic tapes. So for the next months, I was just poring over the code of LCF and marveling at this marvelous implementation of a very clean programming language that was ML. And inside LCF, there was this wonderful compiler of ML into LISP. And then the LISP interpreter would interpret the expression that the user typed in the proof system. And then it dawned on me that since there was this compiler compiling into LISP, why couldn't I compile the produced LISP expression and get some speed up? And lo and behold, it was very easy. So, it was just dumping the expression in a file, calling the LISP compiler on it, reloading it, and I gained a factor of 10. So all of a sudden, this very slow interpreted language was usable as a programming language. So this is how the whole thing started. Right. Mm. But there was no other ML around. So next, we kind of isolated this ML part out of LCF and we developed it. And I got the attention of other groups like Larry Paulson, who was working at University of Cambridge on the third iteration of LCF. Actually, there was a first LCF developed in Stanford, then Edinburgh LCF, then Larry Paulson started Cambridge LCF, and he switched in favor of our implementation of ML because it was faster. So for a while, I was developing jointly with Larry Paulson. Then a professor from the university, a colleague of mine, Guy Cousineau, joined in. And he managed to incorporate to the early ML recursive data types and call by pattern matching. And this was inspired by work from Rod Burstall and Dave McQueen. They had experimented Rod Burstall at some kind of language paper called NPL. And then they developed this programming language, Hope, that was basically recursive equations on data types. And so this fit very well within ML. And so this was the start of Camel.
Okay. And so eventually Camel was, actually implemented in 1987. Was there like a spec for the language?
No, earlier than that, around 83, Some other people had interest in ML independently from LCF actually, and the first one to give an efficient implementation of ML was Luca Kennedy, who was at Edinburgh University at the time. He was a student of Gordon Plotkin. And he wrote an implementation of ML from scratch using a new model for closures that was in Pascal, and that was reasonably fast. So in the mid 80s, we had Camel, but we had also this ML in ML for Unix, developed by Luca Kennedy. So Robin Milner, who was at the time working on process algebras, took an interest again in ML. And he decided to set an international effort for standardizing the language. So that was the work on standard ML, to which we participated in the years 83 to 87, let's say. And this was very, very active discussion. There was even a little newsletter called Polymorphism. And so there were lots of researchers actively working at Edinburgh, at Cambridge, at INRIA, of course, and at Bell Labs, where Dave McQueen was working there.
In 1987, when there was a full implementation with automatic memory management, and what was the what were the goals of that specific project, and how did that project evolve from that point on?
No, the first Camel was just...
the first one was in 1983, you're saying?
Yes.
Okay, wow. Okay, so I read some misinformation at some point. I will have to send out a request for an amendment. But let's talk about that implementation, though. Why did you add automatic memory management? Why was that so important?
No, but memory management was on from the start. The whole Camel effort from 83 to 87, this was sitting on LISP.
Okay. Right, okay,
all this
I get
was sitting on LISP.
So LISP did the memory management.
LISP did the memory management.
Yeah. Okay.
But we were unhappy about it because we did not know how to tell the garbage collector of LISP that some areas were static, like closures, for instance. Okay.
Right.
So for years we developed. We were piggybacking on LISP. We had a very good LISP implementation at INRIA. This was part of a VLSI project, and Jérôme Chailloux joined with a very good implementation called LISP.
Right. We'd like to take a moment to thank our sponsor. DigitalOcean offers simple cloud infrastructure for developers. In one click, you can have a mean stack, a Rails application, an Ubuntu box, or another custom environment. Software Engineering Daily is proud to have DigitalOcean as a sponsor because DigitalOcean is the simplest cloud service provider. I've interviewed Moisey Aretsky, who is a founder of DigitalOcean, and he told me that DigitalOcean was based on this realization that other cloud service providers are so complicated. If you want things to be simple when you deploy your application, use DigitalOcean. To try DigitalOcean, go to digitalocean.com and enter promo code SEDaily. That promo code is one word, SEDaily. Now let's get back to our show. You did mention these closures, and I read a quote from Guy Cousineau where he said the CAM model potentially introduced memory leaks because useless values were kept in closures. Is that the difficulty you're referring to?
Now let's see. I did not talk about the CAM yet. So how did the Camel came in? See, I was telling that Robin Milner was interested in giving a standard for the language. And we participated to this research effort, but we did not really go into the standard for several reasons that I may explain if you wish. But at some point, Robin was dissatisfied that we were keeping our own development and not in line with what was becoming the standard. Okay, one of the reasons was the module system. The module system from standard ML was too complex, and consequently, it did not allow a separate compilation. And for me, a module system must, first of all, allow separate compilation. So this was a stumbling block on which we were reluctant to move to the standard. Another thing was that I was not willing to freeze this programming language effort, because I thought this was research. Many solutions were not were kind of halfway, not half-baked, not finished. Lots of interesting developments could still be done. So I did not want to be bound by any standard. So at some point, Robin came to me and he said, Gérard, now we are, I'm serious about this standardization effort. You keep calling your language ML, and could you call it something else? So that's how we came with the Camel. So this came as a consequence of research into the important underlying formalism of all these efforts is lambda calculus. And typed lambda calculus has many disguises. So one disguise is functional programming. One disguise is proof theory. Natural deduction is just lambda calculus. And the third disguise is the what is called the inner language of category theory. So category theory, it's a modern algebra, and it developed abstract notions of what corresponds in the programming world as the product pairing and as the functions. So there is a theory called Cartesian closed categories, which is some kind of equational presentation of type lambda calculus. So we thought it would be fun to base our implementation of ML on a set of categorical combinators that would act as some kind of byte code for our ML implementation. So around 83, 84, this is what we did for Camel. It's to use this set of combinators, and this was the motivation for calling our implementation the categorical abstract machine language. Actually, this was not very efficient. So there was this problem of memory leak, of closure that you mentioned. So very quickly. Actually, we got rid of these categorical combinators, and we compiled rather in the bytecode architecture of the LISP. There was a virtual machine called LLM3, and so we were compiling from ML into LLM3. Okay, so this is the state of Camel up to the end of the 80s, and then we developed lots of libraries and a lot of facilities for doing metaprogramming with clean macros and so on. But more and more, this Camel implementation was becoming some big monster. See, it was an enormous piece of Lisp.
Yeah. So what were people using it for? What kind of applications were they writing?
Well, the main application we were aiming at was this proof system. So
Right.
this implementation of higher order logic that we call the calculus of constructions, which was ready about 1985. Okay, and so the whole implementation of the system, which is now called Coq, so this has been it's a 30 years old effort that is continuing in ML. So at the time, this was our main application. But we were also using ML for teaching. And the important point was when Xavier Leroy joined the team as a student, and he and his colleague Damien Rodriguez, they really did a brand new implementation of Camel from scratch, completely independently from Lisp, and with a smart garbage collector that would know about static area and would work with generations. So all of a sudden, we had a real programming language that was not sitting on kind of enormous dish of Lisp spaghetti, but fast C implementation of the language. So in that, of course, we use the old Camel for bootstrapping, but very quickly the new implementation was taken up, and this is then that we started doing other applications, and most notably for teaching. So this was called the Camel Lite. So Camel Lite was used quite intensely in teaching in the 80s.
Right, and so there was Camel Lite, and there was also Camel Special Lite. What did these? How did these differ, and what kinds of extensions did these offer?
Well, you know, I mean, it's hard to explain these things because lots of them are kind of inner jokes that are hard to understand. How did Camel Lite come about? You know, Xavier Leroy was young student full of energy, and he was very proud of his new implementation. So he called it Zinc. So I asked him, why are you calling the new implementation Zinc? He said, "Oh, Zinc is not Camel."
That's funny.
So that's funny, but personally, I thought this was a kind of wrong idea because this would this was prone to have some kind of dissensions in the team. So I convinced him to keep Camel in the name. That's how we came up with Camel Lite. Okay, so this was a joke with the cigarettes, of course.
Right. Okay, that's what I thought.
And then we continued the joke with Camel Special Lite. And at the time, we were even using the logo of Philip Morris Company. So
that's funny.
We are lucky that we did not get into an illegal dispute. We had,
so after Camel Lite and Camel Special Lite, eventually you got to Objective Caml, Objective Caml was created. What new features did Objective Caml bring to the language?
Okay, so one short-lived name was this Camel Special Lite. Camel Special Lite was very important for two reasons. One reason is that Xavier Leroy invented a new version of module, which this time allowed separate compilation. And what was quite convenient to have general parametric modules called functors and so on. So this was really a very important development of modular programming. And the second one is that he was working on optimizing compiler. So we had this Camel specialty. It was an implementation in which you could develop interactively code that would generate bytecode, but you could also use the optimizing compiler and have very good performance. And furthermore, there was a facility for marshalling values between Camel and C. So we could build efficient libraries in C and link them to the main implementation. Okay, so this is really where I think we got a very strong programming language. The object-oriented features, which finally gave their name to the language, I'm not so sure that they are so important, actually. For instance, personally, I've never been enthused about object-oriented programming, and I've never used the OCaml features about objects.
Why not? What do you have against objects?
Well, first of all, objects, it's not... I mean, in programming, you have fundamental data structures and fundamental control structures. But objects is something that that came with small talk, and there was a lot of hype, and then there were lots of object-oriented programming languages, and none of them were compatible. I mean, it was different semantics of parameter passing to this object and so on. So, I mean, to the point that that Java and JavaScript are two object-oriented programming languages, but they are completely different as to what is the meaning of.
Well, there are ways of introducing compatibility. I mean, could just pass JSON between them, or you can invent these DSLs that serve as communication platforms between different languages. It's maybe not very elegant, but it does the trick.
But look, once you have a programming language in which you have functional values and in which you have records, then just put some functional records as some fields of your record, and then you have an object. Okay, so it's not a big deal. I did not see that as a programming language feature, but more as a programming style. And then you have this idea of classes and subtyping, and this is where these programming languages differ. But I mean, at the time, there were so many people in software engineering pushing for object-oriented programming, and I was never convinced, because it was claimed that these programming languages were better for modularity. And I don't believe so. See, when you have a hierarchy of classes, then somehow this is a big global object in your programming. So in some sense, it prevents modularity.
Suppose that's true. I don't know. So you never liked You just never worked with object-oriented
No,
programming at all, or you worked with it,
no,
or?
yes.
Oh,
Well, even in Objective Caml, I've never used. I mean, I'm still
oh.
programming a lot with OCaml. I've never used the object-oriented facilities.
What are the other features about OCaml that are appealing?
It's a very good implementation of lambda calculus. Okay, so
I see.
I'm a lambda calculus fan. So from the point of view of applicative programming, it's great. But it allows also imperative. It has imperative features, but imperative features they show like assignable variables or data structures. It shows in the type, so you can you can identify properly the parts of your programming where you're using imperative features.
Okay.
Then it's well interfaced with C and well interfaced with the Unix library. So you can program if you want at low level, and you can profit of the optimizing compiler. So Xavier has done a lot of work on optimizing compiler for the various architectures. So this is a strong point. And so you can marshal back and forth, so you can link with any other piece of software through some kind of C linking.
Okay. So, I'm kind of curious about just the challenges of building a functional programming language or building out an implementation. I mean, what when you were managing the Formel project, what were the managerial challenges and the technical challenges that the project presented?
The technical challenges, I mean, these are, the scientific challenges, yes. So you have some kind of state of the art of the theory of how to best implement lambda calculus, but you have also state of the art of technology, how to take advantage of the current processors and so on. So these technical challenges, they are solved by researchers, and the best researchers are the brightest people. So the role of the manager is more or less to guide, first to attract the best students, and then to guide them in the proper directions. My way of managing the various software efforts I've started over the years were some kind of general model is that I start programming some prototype of some ideas. And it's only when I have ideas that are mature enough so that I'm interested in transforming the prototype into some kind of large-scale programming effort that I involve other people, students,
okay,
colleagues.
Interesting process. So I'd love to talk some about your current work. Your current work is in the numerical humanities. Could you define what numerical humanities is?
Okay. Now you're going at the end of my career. So in between, I did a lot of research with the Coq team on programming environments. And perhaps we should say a few words about that, because in a way this is parallel to the functional programming effort. See, the formal team was working on these both aspects. So there were researchers working on functional programming and the Camel implementation, and there were others working on type theory and higher order logic and the proof system. But this was a very interesting period from a theoretical point of view, because we understood the Curry-Howard isomorphism. The Curry-Howard isomorphism is this similarity between functional programs and proofs. So this opens all kinds of perspectives. It's basically it tells you that programs are like skeletons of proofs of their correctness. Okay, so this correspondence goes back and forth. That is, if you want to prove a program correct, then one way is to intersperse assertions in the program and then try to develop the proof of correctness of verifying the assumptions and the invariants using the program itself as a skeleton of its proof of correctness. Okay? And the other way is that if you develop some general proof in mathematics, then the constructive part of the proof constitutes some kind of executable program. Okay? So this shows most clearly with proofs done in natural deduction and programming done in functional programming. So at the end of the 80s, the formal team split, and one part of the team called the Crystal, they continued the work on OCaml, and the other part of the team worked on this proof assistant Coq. So this is what I did until the end of the 90s. Then around 2000, and I had taken some rest from research. I had some kind of more administrative position at headquarters. And after 3 years of that, I came back to the lab, and I was kind of free to go in other directions, since all my dear students had graduated, so I was free to investigate other things. And I'd always been interested in linguistics. And there was another collection of functional programming and type system into semantics of natural language. So I investigated this at the beginning of the 21st century. And then I focused on one language of ancient India that is called Sanskrit, which is a very peculiar language. It's not really a natural language. It's a language that has been refined by an ancient grammarian 25 centuries ago. So Indians had really advanced views about language, and they developed grammatical tools, and they kind of froze some kind of semi-formal language called Sanskrit. And so I got interested into analyzing this language. Then there was a technical problem to overcome, is that the written form of the language is actually fully phonetic. There are phonetic laws that are followed in the writing of the language. So consequently, a written Sanskrit sentence is a stream of phonemes where the word boundaries have disappeared. It's not like in French or English where we have separate words that are separated with blanks. In Sanskrit, the words, they kind of merge together by phonetic processes. So that's the first difficulty to overcome, is how to find the words in the phonetic mess. And so I looked at this technical problem, and for that I developed original views of using finite automata, but along applicative methods, using functional programming, so using OCaml. So this was the start of this endeavor.
So what are the parallels between creating programming languages and your current work with your current work on Sanskrit?
No, I don't see much
Oh.
connection here. I'm sorry. There is a lot of similarity between designing functional programming language and designing proof system.
Mm-hmm.
And the key to this analogy is the notion of types. Okay?
Mm.
So to come back to this analogy between the proofs and the programs, in this analogy, the types of the programming language, they are the propositions of the logic. Okay, so you can see
Mm-hmm.
the types of programming language as some kind of logical language of the poor. Because you, for instance, you don't have quantifiers, or you have very special quantifiers. You have quantifiers of logical variables in ML, that is this polymorphism. And we did not mention that explicitly, so I want to stress that this is a very important feature of ML, is that it's strongly typed, but it's typed with a type system in which there is a notion of most general unifier. So there is, if two expressions can be made similar and recognized of the same type, then there is a most general type that accommodates them. So that means that ML is typed, but the programmer does not need to put the types in his code. It's the compiler that generates the most general type that is consistent with the program. So that's a very important aspect.
Sure.
So once you see that the types are the propositions, now you can try to go in the direction of having stronger programming language that will be actually languages for proofs. Okay, and
sure.
And now if you so if you want to have types with quantification in the sense of first order logic, then this leads to the problem of what's called dependent types. So dependent types permit you to write like a function that takes two arguments. The first one is an integer, and the second one is an array of length, the integer, that was the first parameter. See, the type of the second argument depends on the value of the first one. Okay, so this is an idea that has not percolated yet in a practical way in programming languages. But in a sense, it's a feature of the future. Because if we have that, then we don't have to do anything special about stuffing logic in your program in order to have proofs of correctness. It is the program itself that has the types that are strong enough to express all your invariant, all your logical specifications. So that's very appealing. But there are many technical issues here, because if you go into such strong types, then there is no notion of most general type and so on. So you must somehow give a notation for the compiler and this kind of thing. Okay, but but many people are actually seriously considering our proof system Coq as some kind of prototype of a programming language with dependent types.
Gérard, thanks for coming on to Software Engineering Daily. It's been a pleasure talking to you about Camel.